now I just start recording. Okay. Yeah. So now let's see. I mean, since I mean we are seeing the length of the ruler is from the previous number to the next number, right? So the length of the ruler is greater equal than 1. So do we guarantee that if the previous number is a and the a plus l will be a new integer? Is that true or false?
Yeah.
Okay. So if this is a true, right? So now you can see. Let's calculating the difference, right? Let's calculating the L. Let's just take out the floor function, okay? So a plus 1 square over 2011 minus a square over 2011 equal 2a plus 1 over 2011, right? So this is the length between the from first number to the next number, right? So our critical point is we want to see at which condition, at which point we're starting to get every time we get a new integer, right? So
we're already like halfway through the meeting limit.
Yeah. So how do we calculating that? How do we calculating from which point every step we're starting to get the new numbers, Jonathan? Sam, this should be greater equal than
1.
1. Okay, so now you get a is equal to, is that 1005?
Yeah.
Okay, so that means from the 1005, right, we are starting to have every number will be a new number, right? So now let's count it. So from a equal to 1005, right? From then on, so from the 1006 to 2111 square over 2011 over 2011, every number will be a new integer.
Why are you taking out the floor function?
Oh, I can add the floor function, right? But if floor function is a new integer after jumping, right? You can think, if I add in the floor function, right? The next number will be the a plus the l, right? The first number is a, next number is a plus l. So this is the length of the ruler, right? At the jumping on the number line. First number is here, is maybe is a, but this is the a floor. Next is a plus l, right? This is the ruler, right? As long as the L greater equal than 1, we can guarantee the next number will be a new integer. Right, Jonathan?
Yeah.
Okay. How I can... Okay, so now you can see, so from a equal 1006 to 2011, we all get new integers. So how many numbers here? So is that 2011 minus 1005 is 1006?
Yeah.
Okay, so let's see what happened before that, right? Before the 1005 square over 2011, right? So my argument, okay, is before that we can cover every integers. Do you agree with me?
Yes.
Okay, because the reason is because here you can see the length of the ruler is less than 1, right? Maybe plus the length of the ruler here, plus the length of the ruler here. You can see that all the rulers can be connected, right? And the length of each ruler will be less than 1, so it continuously, it can exactly cover every integers. So you can calculating what is the integer of this. Let's calculate 1005 square over 2011 is equal to 1005 over 2011 over 1005, right? So this number is very close to 2.0 something something, right? And this number is very close to 5.2 something something, right? 5 something something. So this number give us to what? If this number is a 502.
Yeah.
The first number is 0.
Yeah.
So how many numbers we covered here?
503.
503, right? So what's the total number of the integers we cover?
1509.
Okay, so did you guys get this concept? You can think it's a ruler problem. Okay, you because it mentioned the distinct, so you need to think from which point. Okay, the length of the ruler equal 1 is not, in this case, is when you see the distinct. The ruler length is 1 is a critical point. Okay, so you can see where is the ruler length of the 1, and you can calculate it. Yeah, so let me see the chat. Okay, so Sam and Jonathan, any question on this problem? So Sam, you want me to explain the ruler part? Okay, so you want me to explain the ruler part? Okay. Now let me explain the ruler part for you. So what I mean is, you can think if you have a first number is a, right? Then the next number is the next number between the next number and the first number here. Okay, let's see, you have the a square over 2011. This is the first number, right? And the next number is what? Is a square over 2011 plus 2a plus 1 over 2011. Do you agree with me? Is that right, Sam? Okay, so you can think, so the first number is here, right? And adding the length of the ruler here is 2a plus 1 over 2011. This is the length of the ruler. We jump to the next number, right? So if this length is greater equal than 1, so a and a plus l, when you take the floor functions, I'm sorry, a square over 2011 and a square over 2011 plus the length of this ruler will be different integers. Because the length of the ruler is 1, so it must cover 2 different integers. Did you get it? Any questions, Sam? You get it? Okay, so since you get it, now you can see the ruler length is critical, is
Not really.
not really. Okay, let's see, these are the integer points. Okay, without taking the floor functions, so this is the a square over 2011, right? If we add a ruler length greater equal than 1, right? Greater equal than 1, this one greater equal than 1, so this will be a plus 1 square over 2011, right? So I can guarantee when I take the floor, this one goes here, this one goes to here. They are different integers. Okay, so that means once the ruler length greater equal than 1, that means the number between these two difference, by taking out the floor functions, we guarantee they cover different integers, because here are the integers. Did you get it? Any questions, Sam? Okay, so that means if we get different integers, what does it mean? That means we just need to calculate in the difference of the ruler length, right? The ruler length is the difference between two consecutive numbers without taking the floor functions. That means this one is 2a plus 1 over 2011, right? So where is the point that the ruler length greater than 1, right? So that means a from 1005, right? So what does it mean? Means when 1005 square over 2011, 1006 square over 2011, 107 square over 2011. So the length of this ruler is greater equal than 1. The length of this ruler greater equal than 1, so on and so forth, right? Jonathan, do you have any questions on this?
No.
Okay, Sam, now do you have any questions? Okay, if you don't have any question, you can see from this point, right? Since the ruler length is greater equal than 1, so every point we get a new integers.
Why are you even using a ruler?
Because I mean, I let you understand this is something. The ruler is like the jumping the length, right? The jumping length. Right, so you can see basically we try to cover the number line, right, using a variable. Now the length of this ruler is changing, right? You can see at which point it's starting every time to cover a new integers. So any questions for this problem now? Jonathan, Sam? Okay, no questions. Now we can move on to this one. Okay, it's you can see it's really similar. The answer is here. The answer is this one. Okay, so now you can see it's very similar to the problem of this. I think this is the problem that Mr. Swart talked about in class, right? So you can see for this problem, okay. So for this problem is it mentioned to you that the 2 to the 2013 and the 2 to the 2014, right? I mean the number of this is the number line, right? So before previous problem, right? Every crossing point is an integer. Now this crossing point is 5 to the power of something. So this is a 5 to the power of 8, 6, 7, right? Yes. So, but now let's analyze the problem, and I want you to see the connections between this problem and the previous problem. It's exactly the same concept. Okay, so this, for example, is a 5 of the 8, 6, 6, 5 to the 8, 6, 5, up to the 5 to the 0, right? So now this is the number line. So what you can see here, right? is we are trying to see how many numbers can make this happen, right? So that's what we do is between these two numbers, let's take a log 2 of 5, right? And less than m plus 2, then less than n plus 1 of log 2 5, right? So now you can see, okay, our if we take the log, right? If this is the original number line, right? If we take the log, this will be from 0, 1, 2, 3, 4. It will be an integer number line, right? Let's take the log of the 2 up to the 2013, right? So if we take log, this number line, right? This number line for either for this one is take log 2 is 2013, then 2012, so on and so forth, right? And 0. It's exactly the previous integers, right? Now you can see the we are counting how, so we hope there is m. Let me see. Okay, so we what we hope is we have m plus 1 and m plus 2, right? Between these two, between all this crossing point, right? We wish we have m plus 3 numbers. We have 3 integer numbers between our markers, right? So what is the from the first to the next, from the first to the next, from from all this crossing point, how many segments we have, right? The jumping length is log 2 of the 5, right? And this number is just greater than 2 and less than 3, right? So so that means our jumping ruler length, so that means, I mean, between these two, we either have 2 points or sometimes we have 3 points, right? So we trying to know how many segments we have such of the 3 points, right? It's exactly the same concept as before. So we are taking a look at the jumping length is this. This is our jumping length, right? In this jumping length, sometimes we cover 2 integers, sometimes we cover 3 integers, 2 integers or 3 integers. This is the ruler of the length. So now you can see it's very similar. So we can assume we have X segment cover the 2 integers and the Y segment cover the 3 integers. So the total number of the segment here, right? Because the last number we have is 867, right? So that's why we have 867 segment. This is the total of segment, right? The next is some segment cover 2 numbers, some segment cover 3 numbers, right? So 2x plus 3y equals the total number, total 2 of something number has been covered within 5867, right? So the total number has been covered since is 2 power to the 1, right? Up to this. So is that 2013? Yes. Yeah. So this is exactly as Johnson, right? So that's why, I mean, by solving the equations, we can get this, right? So you can see this is a jumping here from here to here. It's a constant length. of the ruler, right? That's all the crossing mark, and each crossing mark we cover either 2 integers or 3 integers. It's the did you see that Jonathan and Sam? Did you see the connection between these two problems? They test the same concept, I think.
Yes.
Jonathan, what do you mean 6 minutes left?
This meeting can last at most 40 minutes.
No. This is the team. There is no such limitation now. Okay, we can go on as long as we can. Okay, this is that is work meeting, so no such limitation. Okay, so now let's go see some problems. I think this problem. Okay, so Jonathan and Sam, Jonathan cannot solve it. Sam, can you solve it? Okay, I think let's start to talk about this problem. Okay, so for this problem, okay, so what we know is such the floor sequence problem. Okay, 101 plus 2 square of 101 plus so on and so forth, 100 square over 101, right? So every floor function can be write as a n square over 101 minus the fractional part of the n square over 101. Yes, Jonathan is right. So we can write it in this way, right? So now we can do the summation from n equal to 1 to 100, right? So the first part, anyone have the difficulty on the first part? This one is quite trivial, right? Now this one part is 3350. Okay. Now the difficult part is the second part, is a minus n equals 1 to 100. Fractional part of the n square over 101, right? So I ask you guys a question, okay? For example, I mean, yeah, for every number, okay? So every number here, okay, basically is n square over 101. Does this equal to the n square of mod 101 over 101?
Yeah.
So basically you can see we are trying to, once we figure out the pattern here, okay, once we figure out the n square mod 101 pattern, 101 pattern, we solve the problem. Okay, so now how do we find this pattern, right? So now the next one is 101 is the prime number. Okay, I need to introduce a concept called the primitive roots. Okay, so Mr. Sword in his homework solutions, okay, he already gave you guys introduce this type of the concept for you guys. Okay, let me introduce with a simple example of the primitive roots. Okay, so let's do 101 is so big. Okay, can we use the 7 as example? Let's use the 7 as example to talk to you guys what is the primitive roots. Okay, so for the 7, right? I mean the residual of the mod 7 is not, we don't talk about the multiple of 7 is 1, 2, 3, 4, 5, 6. Right? So you now we can do This is the a equal all this, right? What we do is a to the power of 1, a to the power of 2. Sorry, let me erase it. Okay. A to the power of 1, a to the power of 0, 1, 2, 3, 4, 5. Okay, so what is the 1 to the power of 0 mod 7? Or mod 7, right? Is that 1? What's next one, Johnson and Sam?
1, 1, 1, 1, 1, 1, 1.
Yeah, Sam, you can feel free to turn on your microphones. Okay, you don't have to type every time.
1,
So,
2, 4, 8, 16, 32, 64.
1, 2, 4. 1. Johnson, can you calculate? 8 mod 7.
1.
1.
2, 4.
Next.
3. 2. 6. 4. 5. 4. I mean 1.
1. What's next? No, you are wrong, Jonathan. 3 power to the 0. It's 1.
So
3,
we just move everything down the
2, 6, 4, 5. Because the Fermat-Little theorem tells us what? A to the 6 must be what?
1.
Fermat-Little theorem tells us it's all ones. Okay, I give you such. Did you see? I mean, what's the length of this cycle of the roots of the 1? So the 1 order is 1. Do you understand? The order means the length of its cycle. Yeah. What is the 2 of the order? Order of the 2.
3.
3. What is the order of the 3? Is that 7? So 7 is the primitive roots in this case. I mean, 3 is the primitive roots of mod 7. So what I mean here is if you have a number called 101 is a prime, there exist primitive roots between 1 and 100 such that, okay, the g of the 0, g of the 1 to g of the 99 will cover is a permutation of the number of the 1 to up to 100. Any questions on this, Sam and Jonathan? Do you have any questions, Sam?
No.
Okay. So Sam, you can turn your microphone if you want. Okay. How it is 7? Who typing? Sam? What do you mean how it is 7? No, it is. Oh, it is broken. It is 6. Yeah, it is 6, right? Yeah. So, any questions? Order 3. Order means here. So order. Oh yeah, order. I mean, sorry, it's 6. Yeah, order 3 is 6. Yeah. Yeah, I make it wrong. Thank you for pointing me out. So now you can see. Now you can see there is a primitive roots, right? So this one will cover every number, right? that means if G of the 100 is 1, right? So what is the G of the 50? Mod 101. Can it be 1? Same questions. Okay, my question is the primitive roots, right? G of the 100, G to the 100 mod 101 must be 1, right? This is the FLT tells us, right? If G is the primitive roots, what is the G of the 50 mod 101?
100.
G of the 50 is yes, this must be negative 1. Otherwise, it would not be a primitive roots, right? Yeah. Yeah. So now let's see what happens here. Because what we are going to analyze is we want to see the n square mod 100, right? So our goal here is trying to figure out the n square mod 101 pattern, right? So now you can see the n is some number 1, 2 to 100, right? So that means I can have a G, right? So it's corresponding to a G to the 0, G to the 1, to the G to the 99. Any questions about this? After you permutating, no matter how you permutating, it must be the primitive roots of the power. Okay, this is the map between the n and the g, right? So how do we map the n square? Is that 1 square, 2 square, over 100 square? Somebody tell me, what should I write here?
G0, G2, G4, all the way to G98.
Okay, it's G0 times 2, G1 times 2, all the way G to the 99 times 2, right? The same as Johnson says, G0, G2, G198. Okay, now if we have this, right? What I want to show you guys is, can we pair?
Why does a primitive root always exist?
It's guaranteed. Okay, I just use this one to show you guys. Okay, I mean, if it doesn't guarantee, it doesn't happen, that means you won't have a cycle of the length of the you won't have a cycle of the length of the prime number -1. That's not right. Okay.
What's wrong with having a cycle what's wrong without having a cycle of length n -1?
That means it's this number is not a prime. You must can decompose this number to two smaller numbers, because every prime number must have a full cycle. Understand, Jonathan?
Yeah.
Okay. Next is I want to show you, okay, because everything here is g to the power of 2 something, right? So we exist a pair that g of the 2a and g of the 2b
equals 101.
Can be mod 0.
101.
Okay, so let's see how such things exist. Okay.
21.
So if we take out the g of the 2a without loss of generality, let's say a less than b. So what do we have to here? G of the 2 of the b minus a, right? Any problem on this one? So think about it. G of the 2a, can G of the 2a
now clearly that G to the 0 plus G to the 50 is 0.
Can this be mod 101 be 0?
No.
G of the 2a, no way, right? Because we are talking about 1 square, 2 square, 100, 100 square. No number is a multiple of 101, right? So now we need G of the 2 of the b minus a, right? Need to be -1 mod 101, right? So do you know which number, G of the which number is -1 mod 101? Yeah, G of the 50, right? So you know G of the 50 happen with this. That means b minus a equal to 25, right? So now we can write our numbers. This is our residual numbers, right? We can pair them. For example, you can say G of 0 can be paired with the G of 25, right? And this two with the residual, one is t with over 101, and the other must be 101 minus t over 101. And these two numbers add together equal what? The fractional of these two numbers add together equal what?
The fractional of those two numbers, 0.
For the fractional number, for example, this is the 0.1, this is 0.9. Is that 1? Any questions on that up to here? Any question, Jonathan? Is this right?
Yeah.
Okay, so what's the next pair? G or power to the 1 can be paired with
G to the 26.
And the G of the 24 can be paired with
G to the 49.
What's the next one? Can we do G25?
No, we need
It's already
the
here.
G50 and G75.
G75. What is the last one? $74, right? Here's 75. Pair with the G of the what?
G of the
99. Yeah. Did you see every pair will be 1?
Yeah.
Now how many ones we have? Yeah, I know chat is slow. It's okay, Sam. You already so great. So is that 50? So now, based on our analysis, what's this part?
50.
Subtract 50, right? So what's the answer?
3300.
So any questions on this problem? This problem is a little bit hard because it's the square, okay? And but we still need to use the primitive roots concept here. I can go down. I can go down. So whenever you see a prime number, okay, the number between 1 to 100 itself is a permutation of the primitive roots power, okay, power 0, 1 to up to 100. Then we can play with using the Fermat-Little theorem and and also the primitive roots is the longest cycle. So that means if 7, right, means G6 must be 1 and G3 cannot be 1, okay? Otherwise, it's not primitive roots. How do you know G0 and, okay, here. Did you see what I'm going to find for any of the G of the 2A? We can find of the G of 2B is 0 mod 101, right? And all the fractional number we are talking about is between 1 to 100, right? It cannot above the 101. Yes. So are you clear, Sam? And are you clear, Jonathan?
Yeah.
Okay. You guys clear? Okay. Okay, let's see. What's the next problem? I think this problem is not hard, and let's solve. Okay, maybe let's solve this problem first. Johnson, can you solve this problem?
No.
Or can you solve this problem, Johnson?
No.
Okay, now let me solve this problem first. Okay. Oh, Sam can solve. Okay, Sam, can you bear with me? Let me go back. Go back to which one? You. Oh. I still don't understand the one bit previous. You mean this one? Which part? Last? What is the last? Like how you pair. Okay, how we pair. Did you see? I mean, the once the b minus a. I'm sorry. It's 0 times 2 pair with 25 times 2. 1 times 2 pair with 26 times 2. I mean, did you see G of the 2A and the G of the 2B must be paired now, right? And the B, the difference between B and A is 25. My wrong. We should write a times 2, right? Okay. Any questions, Sam? Okay. So now bear with me a little bit. Let's solve this one first with Jonathan. Okay. So Jonathan, let's see this problem. Okay. So the number A is P over Q, right? P and Q are relative prime positive integers. PQ belong to positive integers and relatively prime. Okay, so have these properties. Okay, so Jonathan and Sam, I think, do you familiar with the if I write as y equal this, do you know what the picture looks like?
No.
Okay, Jonathan, you need to be very think about it. Okay.
I think I have an idea of what it looks like, though.
So we always write 1, 2, 3, 4. Let's draw up to 4, and also let's draw some negative ones. 0, -1, -2, -3, right? So what's the range of this, Jonathan?
The range
of this?
0 to 1.
Can it including 1?
No.
No. So that means, think about it. What's the first, in the first section, what it looks like?
A 0.
A 0. In the second section, what it looks like?
1.
Up to 1, right? In the third section, what it looks like?
Up to 2.
Like this, right? Next one.
3.
Okay.
And the same thing for the other side, just a reflected.
What's this?
Down to -1, down to -2, and down to -3.
Down to -1, like this, right?
Right.
Right, Johnson?
Yeah.
Okay, so now you can see this is the what this is the x floor times x. Okay, what is the a times x squared looks like? And remember, a equals p over q, and pq are positive integers. It's open up or open down?
A times x squared opens up.
Opens up, something like this, right?
Right.
Something like this, right? So the intersection between the two, can it be on the negative range? Can it be on the negative range?
No.
It must be on the positive range, right?
Give yourself a sticker.
He said G.
Right?
We're having a good dinner and playing piano.
Did you see there is a intersection in each segment?
Where?
Johnson, did you see it?
Yeah.
Okay, now let's see x equals n plus x, right?
Let's go.
Right? So what we want to find is n times
Important.
x, right, equal a of the n plus x squared. Am I right, Johnson?
Yeah.
Okay, now what do we have? I mean, you want to solve all these connection points, right? So as long as you solve the fractional part, did you solve the problem?
Yeah.
Okay, how do we solve the fractional part? I think you can expand as a what? It's a quadratic, right, Jonathan? Jonathan, what are you doing? How to solve this quadratic?
Quadratic formula.
What's the discriminant?
2an minus n all squared minus 4a times a n squared
Equal what?
equals n squared times the group 2a minus 1 all squared.
Get it, Jonathan?
Yeah.
Then what is the fractional part?
The fractional part is denominator 2a, numerator n minus 2a, n plus or minus square root of n squared times that.
Okay, in the test, I tell you in the test, how do you pick plus or minus? Okay, I tell you, okay. So if you think this number goes here, right? Normally it goes too slow. So, I mean, the thing is, if we need to check, okay, I tell you, but in the test, you need to have a feeling. In order to have this number to be positive, do we need 1 minus 4a be greater than 0? What do we need about a?
A is smaller than a quarter.
A is less or equal than a quarter, right?
Yep.
Yeah. Yeah. So if you pick the plus, it will increase very fast. Okay. But we wish it increase slow. So normally we are going to take the minus in this case, because the only thing you need to check, what do we need? X need to be greater equal than 0, less than 1, right? So
Yeah.
so you can think n, okay, 1 minus 2a minus n root 1 minus 4a. So you tell me which number is bigger. 1 minus 2a is bigger, or root 1 minus 4a is big?
1 minus 2a.
So this is greater than 0, right? Am I right, Jonathan?
Yeah.
And these two numbers are very close, right? Are they very close,
Yeah.
Jonathan? Yeah. So let's go check the other one, okay? I want to show you, because we have time, and I want to show you. In the test, I will get rid of the positive directly, okay, without thinking too much if I don't have time. But since we have time, we can compare this one with 1. Okay, does that mean we can compare this number plus 1 minus 4a with 2a over n?
Yeah.
Does that mean we can compare 1 minus 4a compare with the n of the n plus 1 of the 2a minus 1?
Yeah.
Does that mean we can compare 1 minus 4a, remember a less or equal than a quarter, versus the number, let me write it down, okay? So it's 4a squared, then n squared n plus 1 of the square, minus 4a n plus 1 over n plus 1. Does that mean we can compare, take out this, right? So we can move this one here, we compare 4a over 1,
Samuel
4a
just
over n.
raised his hand.
Excuse me? What happened, Jonathan?
Samuel just raised his hand.
Why I cannot see it? Let me see. You can see it. Let me see. Participant. You know I should use that room. So I have 2 screens. Now I only have 1 screen. Where is the participant? People. I didn't see Sam raise the hand. Okay, still go to chat. Jonathan, did you see this?
Yeah.
This is compared with the 4a squared, the n plus 1 of the square over n squared, right? It's equivalently to compare 1 over n. Is that 1 over n? Times n. Oh, okay, we can times n here. It's really compare 1 over a times the n plus 1 of the square over n, right? Then it's a times the, we can put this one here versus a, then we have 1 over 1 plus 2 plus 1 over n. Is that true?
Yeah.
Okay, if this is the true, Sam, what happens? You say hello? Nothing? Okay. So, Jonathan, this number, right?
Yeah.
This number means this number means what? This, I mean, what is the maximum number of this one?
Maximum.
Maximum means new denominator be smallest, right?
Then n would
Is that
be
1 over 4?
yeah. You said denominator is smallest.
A denominator is the biggest.
Yeah. Minus WD.
Minus WD. Okay.
That's what Samuel said in the chat.
Where is the chat? Okay. I think when I do the analyze, I find the I find the contradictions on this one. Let me check it. Okay. So once I find the contradictions, then I do pick the negative ones. So that's the so it's n, so the x is equal to n plus of the 2a n 1 minus 2a, then minus n root 1 minus 4a. Okay, so what's this number, Jonathan? Is that n of 2a? Then it's 2an, 2an. Is that n minus n root 1 minus 4a? Right, Jonathan?
Yeah.
Do you understand this? Jonathan, where are you?
I understand.
Okay. So is this equals this?
Yeah.
Okay. Now you find the each intersections, right? That's all the roots. So take a look. It mentioned all the real roots. Okay, so the sum of all the real roots is 420. How are you going to deal with that, Jonathan?
Can I see the solutions?
Here, n over 2a, n over 2a, 1 minus root 1 minus 4a is each one, right? Is each solution, right?
Yeah.
So we can starting from n equals, right? Is that n equals 0? Is the first one? That's here, right? Up to what? Up to n minus 1, right? Let's assume there are n numbers, right?
Why are you writing a capital N?
Or m. Is that okay?
Yeah.
To m, that equals 420, right?
Yeah.
Right. So now you can think is this is the m minus 1, this is the m, right? You have this. This is the last intersection you have, right?
Yeah.
For the next one, you cannot have any intersections, right? Okay, now let's do it. So this one is equal to the m times m minus 1 over 2 times 2 over 2a, 1 minus 4a equals 420, right? Okay, so this number, okay, this number is great or less than 1?
Yeah.
Greater or less?
Less.
You can converting it. Okay, let's do the 4a. Let's do the 1 plus. Can we do this?
Yeah.
That equals 2 over what? 1 plus.
1 plus.
This is the 1. How about this number? Less than 1?
Yeah.
So this is a 1 plus some number less than 1, right? So this number greater than what?
1.
So in order to have this number times some number greater than 1 to be 420, you want this number to be less than 420 or greater than 420?
Less.
Less than 420. That means you need to find this number is less than 840, but very close to it,
Less
right?
than or equal to.
Yeah. You can find this number, right?
Sort of like 30.
Okay. You mean 30 times 29?
That's 870.
Yeah. What's next?
29,
How about
which
29
I
and 28?
already 29, which I already know which works.
29 and 28 works, right?
Yeah.
Okay. So if 29 and 28 works, you can apply this number in, am I right?
Yeah.
So that means
Wait,
1
how do
minus
you know that M is 29?
You need to be really close because A needed to be here.
Less than or equal to a quarter?
Yeah. So now you can do the 420, right? Over what? Is that 29 times 14?
Yeah.
Now can you solve the A?
Yeah.
Okay. If you solve the A is equal to A equals 29 over 900.
Yeah, I need to use the bathroom.
Is this number less than a quarter?
Yeah, of course it is.
Yeah, okay.
I need to use the bathroom.
Okay, come back quickly, okay? So Sam, I mean, what's the next problem you wish me to talk? Last 3. This one, and this one, right? Okay. After Johnson come back, we talk about these 3. You ready? Okay. OK，再讲3道题，今天先这样，明天继续。
Finish. Go to your bed.
No, I want to sleep with you.
No, man, you by yourself. Okay.
I want to sleep with her.
Say no, let's get out of her. I'll kiss you goodnight.
Okay, let's start. I'm sorry, I mean that Jonathan take a break. So let's starting to solve this problem. Okay, so whenever you see the ceiling and the floor functions problem, right? So in this problem, my first thinking is it mentioned all positive real. Positive real and x less or equal than 5, right? So for here, what my thinking, you know, I mean, for the floor or ceiling, right? The most common thing is we want to solve some equation. Mostly is a quadratic equation of the fractional part. Hold on. Can you see 10 again? You mean this one? Go up. Up. Down a little. So any question here? No, okay. So normally we try to solve the a quadratic equation of the x, and we know the x is ranging from the 0 to 1, right? And the x must be like a function of its floor, its integer part, right? By solving the bounding the zero the fractional part, we can bound the range of the integer part. For example, from A to B, right? But by bounding the range of the integer part, you know if it is A and B, so it, for example, A is 5.6 and the BB is 10.9. So you know we can only try 6, 7, 8, 9, and 10. Right? So then you can apply the 6 to this equation again to see what is x, 7 to this equation again to what is 7. So this is a common way, okay? It's a very common technique we use to solve the number with the integer and the floor, because you know the range of the fractional part. So that's why we want to solve what the fractional solution is. Then using the bound of the fractional, we bound the integer. Then we apply the integer back and to solve each fractional. That's how it works. Okay. So for this problem, let's do if x belong to integer first. Let's see if x integer, right? X equal x squared plus x squared over 2x equal x. That means it's always work, right? So that means the solution is equal to 1, 2, 3, 4, 5. What's the summation of this? 15. Okay, this is the case 1, right? It's trivial. The case 2, let's say x belong to not belong to integer, right? But x belong to that, x belong to fractional. Let's me write x is equal to n plus delta. That means delta must be greater than 0 and less than 1. Okay, so in this case, let's write this number again. Is that n plus delta of the square, then plus the ceiling will be n plus 1, right? The floor will be n, right? What is the denominator? 2n plus 1. Do you agree with me, Jonathan? And do you agree with me, Sam? That equal n plus delta, right? Okay. Oh yeah, I mean I considering the integer because I want to check what happens with the integer, right? Is Jonathan here? Yes, Jonathan is here. I think Jonathan is the next. Jonathan is in the next room next to me. So any problem for this one? If you don't have problem now, the next step is we just reorganized this problem. Okay, we just try to make it try to make it I mean, an equation related with related with the delta. That's the fractional part. Okay, so let me simplify it to you. It finally comes to 2n plus 1 times the delta is equal to then 2n plus delta times delta. Okay, so you guys can think, okay, if this one equal this one, right? Right hand side is what? Is an integer, right? That means this part need to be integer. What kind of delta can be? That's my question to you. This cannot be irrational, right? Must if 2n plus 1 times the irrational number, can it equal the integer? So what kind of number can make it integer, Jonathan and Sam? Rational, how to represent this rational? Yes, A over B, but what kind of B? What kind of A? Can we write as this? What's the range of the M? Now you know the left side is M, right? Now you can apply this part to the right side, right? Okay, let me give you what's on the right side. It's M. Okay, it's a 4n squared plus 2n plus m over 4n squared plus 2 plus 4n plus 1. Okay, think about it. This m is an integer, right? Do you think if m is less or equal than 2n, if m is really close to 2n, this number, this part is greater than 0, less than greater than 1, less than 1? What's the range of this the number I box using blue? Is this number less than 1 but greater than 0? So you can think left side is M, this side is M, right? So basically you wish this part ceiling up to ceiling will be 1, right? So M will equal, right? So we know the 4n squared plus 2n plus m over the 4n squared plus 4n plus 1 up to ceiling is 1. Am I right? Okay, so now you know m delta equal m over 2n plus 1 works for n, right? So you think all the solutions, if I fix the n, right? So all the solutions of the m from what to what will work. We just talk about it. What's the range of the m? Cannot be 1. Yeah, well, it's 1 to 2n. Did you get it, Jonathan? Sam already get it. Did you get it, Jonathan? Huh? You didn't get it? Did you see this one? The m and m equal this one's m times ceiling of this number, right? Did you see the? Yeah. Do you agree the ceiling is 1? So what I mean is basically we find the solution that m equals 1 to 2n all works, right? Can we sum it first? What is the sum? How many n's we have? What's the sum of this number? Either Sam or Jonathan. And you don't care, Jonathan, what's this? Focus on what you need to do. Sigma n? What do you mean sigma n? We are summing through the m. N kicked out. Yeah, why you have the n is a constant, Jonathan. How many n's you have? Jonathan, what is this number? Equal what? Is this a constant? You be careful, okay? You should know this. Is that 2n squared plus what? Take out any constant, take out anything not related with the m, then do the m. What's that? What's this number? So you know if you're starting with the n, right? Between n to n plus 1, all the fractional adding together equal to this number, right? What is the range of the n? Remember, x need to be less or equal than 5, okay? Can n be 5? No, 5 we don't have 0 to 4. Then you guys check this answer. The final answer, forget, is that 85? It's 2 of the 1 square plus 2 square plus 3 square plus 4 square, right? Then plus the 1 plus 2, 4, right? Okay. Can you go up? Yes. This one, since x need to be less or equal than 5, right? And we are talking about all the fractional. Yeah. Jonathan, do you understand this solution now? Sam, you understand it? Go down a little bit. Okay. So next one. So next one, okay, how about we talk about the last proof problem first? Okay, so it means n is a natural number. We still have more, Jonathan, okay? We still have something you cannot solve. But maybe Sam can solve, okay? But Sam, if you want to join us, you can join for our next session. We talk about the rest of the problem. And there is one problem, this one, Jonathan, I think his approach is much faster than what I did. So let's talk about this first, okay? So n is the natural number, is positive integers. We are going to prove this. Which dismiss button? Okay, no problem. Okay. We can still, I know because I set to 100 to 9 o'clock something, but it's okay. Okay. See previous. This one. Go down a little bit more. Any questions? Okay. Yeah, so this one. So this is the proof problem. Okay, this is the Olympiad level. So now let's see. I mean, we want to prove this is an even number, right? So what you can see, okay, if I set Sn equal to n over 1 plus n over 2 plus n over n, then plus law of the root n, right? Yeah, so you can think when n we change from n to n plus 1, right? N plus 1 over 1, then plus n plus 2, 1 over 2 plus, then plus n plus 1 over n plus n plus 1 over n plus 1. Huh? Why we ask? Because we don't have time to talk about it, and Sam wished me to talk about some problem. He has difficulties, and I think you also have the difficulty. So I pick the problem you both have the difficulty first. Does that make sense? Okay, then you tell me. Okay. Yes, we are doing the induction. Yeah, yes, I'm not on mute. I mean, the Johnson is saying, yeah. So the floor of the basically we are using induction. I'm listening to what Johnson says. It's n equals 1, so we can check the number is 2, right? This is the true. So next is doing the inductive step. So the thing is we need to consider n over 1, n over 2, n over 3, right? So when we increase, for example, from n over k, right? When we increase from n plus 1 over k, right? So you can think this number and this number are really close. Yeah. So n over k is here. We just increase a little bit to n plus 1 over k, right? If n plus 1 over k here, they are the same. The only problem is n plus 1 over k land on the integers. Then this will belong to the previous integer, and this will belong to a new integer. There is a difference between them. Yeah, so the difference between the two is the number of factors of n plus 1. And then we need also plus what? The n plus 1 minus n. Why we need to add 1? Okay, so any question for this, Sam? Floor of the square root minus it's floor of the square root of n plus 1 minus floor of the square root of n, right? That one, I mean, you can think. I ask you, okay, I ask you, think about it, okay? If this number and this number, if n plus 1 just landing on the new of the perfect square, if this is the perfect square and this is the previous perfect square, did you see the difference? They are very close, right? Yes. So now we need to do the casework. The first one is n plus 1 is a perfect square. N plus 1 is a perfect square. What's this number? This is the odd number or even number, the first part. The first is odd. How about this one, Sam? Based on my explanation, right? So we just have all this rounded to the previous one, and you just land on a new square number. Then what's the difference between these two? For example, this one is a 5 square, take the root, and this one is 24. Is that 5 and 4? Is that the only difference is 1? Do you understand this? This is the critical part. Is this even? Now the case work of case 2, right? This is the case 1. Then the case 2 is n plus 1 is not a perfect number. So how many factors it has? Even factors, right? Plus 0 equal So the difference between these two will be even. So did you see it? It will always be even. Yes. Yes. Any question on this problem, Sam? Yes. So the first one is even, right? So the difference is also even, right? So is that always even? Oh, you like this question? Thank you. This question is interesting. Yes. Okay, Sam. I think yes. I mean, can we discuss the rest of them? I schedule another meeting. Is it sometime maybe this week or early next week? Yeah. Let me maybe tomorrow. Let me think. What is Jonathan doing? Jonathan has a speech therapy. So can we do Friday? Can we do Friday? Okay, sure. Let's do Friday. Okay, and if this is the case now, let's stop today. And I wish because tomorrow you also need to wake up early, right? Do you have class today? I think today, I mean, the Jonathan school is off. Oh, you have school today. Okay, Jonathan doesn't have any school today. You do have school tomorrow. You will wake up early. Okay, so in this case, let's stop now. And yeah, I wish you, your brother, and your mom have a great night. Okay, thank you. Have a great night. Bye. Thank you. Let me stop recording.